Hello everybody, in this video we're going to talk about the electromagnetic spectrum of light, or all the possible wavelengths of light. So far, through the notes and through the videos, we have learned that light is an electromagnetic wave. And what really distinguishes one type of light from another is the wavelength of light. Change the wavelength and you're dealing with a different type of light. I'm going to get rid of type and say you're dealing with a different color of light. We're going to base our discussion in the light that the human eye can see, which is just a tiny little fraction of all the possible wavelengths of light. And we'll ground ourselves with that. We will explore what it means to talk about a spectrum of light and expand outwards to understand all the different colors of light, all the different types of light, the entire electromagnetic spectrum. All right, let's dive into the slides, and I will have a short demonstration in this video that you should be able to repeat at home. So what is the electromagnetic spectrum of light? That is our goal. Let's start with some simple questions. Let's start with light that we're used to. We're using wavelengths to describe different types of light, and really what I'm saying, different types of light, what I'm talking about is different colors of light. So right here, I've made ourselves a pretty little rainbow on the screen, but I can ask the question, so what makes this red color red? What makes that, what is different about the light that's coming into my eye from this red color, red light, versus say yellow light or green light or blue light or violet light? So what is the main difference? And what determines the color of light? What determines the color of visible light, the kind of light the human eye can see, is the wavelength of light. Change the wavelength a little bit and we see a different color. That's the only thing that's different amongst all the different colors of the rainbow. So here we have our Roy G. Biv. We got rid of indigo a while ago. It's kind of an interesting story. That indigo is really kind of blue, and what Newton called blue is more cyan colored. But we all sort of agree the human eye can't really see the indigo color very well, or what used to be called indigo. So we don't really deal with indigo any longer. So we have Roy G. Biv instead of Roy G. Biv these days. And what the difference between red and blue is simply the wavelength of light. To the point where red light is an electromagnetic wave. So light is an electromagnetic wave. What is special about red light that makes it look red? Well, it's simply an electromagnetic wave with a wavelength of about 650 nanometers. So here I have the boundaries. So red light is pretty much everything between 625 nanometers and 740 nanometers in wavelength. Notice that we're using the distance unit nanometer, billionths of a meter. So when we talk about the wavelength of visible light, the kind of light humans can see, the appropriate distance between those wave crests is hundreds of nanometers. I could say that's tenths of micrometers, tenths of microns. The two units that are most commonly used for astronomy, when we were talking about wavelengths of light, for the type of astronomy I should say Dr. Lindsay does, are nanometers and microns, micrometers. There are other units of light, and we were about to see that light can have any wavelength. You can talk about light that has a wavelength of 1 meter, of 10 meters, of 1 nanometer. But what makes red light is it's just an electromagnetic wave. It's just light with a wavelength of 650 nanometers, about. What makes green light? Green light, it has a wavelength of about 525-ish nanometers. So if you have an electromagnetic wave coming at you, or a whole bunch of them, so you can actually see them, and they all have the same wavelength of 525 nanometers, you'll see that light as green. Blue light is an electromagnetic wave with a wavelength of about 450 nanometers. All electromagnetic waves, all travel at the same speed, the speed of light. The difference is their wavelength. And if you remember from the previous video, we could translate that wavelength into a frequency. So red light has long wavelengths, the biggest wavelengths, equivalently the smallest frequencies. Blue light has the smallest wavelengths, equivalently the biggest frequencies. So shorter wavelengths to longer wavelengths. And we get all the colors of the rainbow that the human eye can see. So when we do something like this, whenever we take light and we divide it out, we spread it out into its component wavelengths, we just spread it out into all the different colors of light. We talk about all the light spread out by its wavelength. That is what we call a spectrum of light. So when we look at something like this down here, where we're spreading out light from the violet colors all the way over to the red colors, we're spreading it out by wavelength, we're talking about a spectrum of light. This wavelength range is the wavelength range that the human eye can see. It's what we call visible light. So this Roy G. Biv, what you've learned about for pretty much since you've been a child, since you started education, this is the visible spectrum of light. You put all the colors together, combine all the colors, and you get what we call white light. All the colors of light, all the wavelengths of visible light, roughly equally mixed. You can see a rainbow. All you have to do is get yourself a nice prism or wait for a nice rain shower and you can see a rainbow, which will, water droplets are kind of acting like prisms in the sky. But you can shine in white light, and then what a prism will do is it will spread the light out by wavelength, and you can see the full visible spectrum of light. So this white light contains all the wavelengths, and then we can spread it out into a component wavelength so we can see the visible light. What makes this red red is it has longer wavelengths than the green light, and then the blue light and the violet light. So now we have to ask a question. This is a really narrow range of wavelengths, 380 nanometers to 740 nanometers. That's a little over, that's just shy of 400 nanometers of spread. That is a really small amount. 400 nanometers is about 0.4 microns, 0.4 millionths of a meter of spread and wavelengths. That's a really small amount. So we have to ask ourselves, we know that an electromagnetic wave can have any wavelength. So what happens? Why do we stop here? What is redder than red? What is violeter than violet or bluer than blue? So what is redder than red? Well, all of these wavelengths of light, say 800 nanometers or 900 nanometers or 200 nanometers, those wavelengths of light exist. They're all around, well, the 800 nanometer radiation is all around you right now. It's just our eye, the human eye, can't detect those colors. We can't see them. They are invisible to the human eye, but they do exist and they interact with everything around us, just not our eyes in a way that we can see them. So these invisible colors do exist, but what are they? What is redder than red? So if we were to push out in wavelengths to 800, 900, 1,000 nanometers, 1 micron, if we were going to go to frequencies, so these would be small frequencies, so it would be going to even smaller frequencies, would be going below the red frequencies. One might say that we're going infrared, meaning below red, if you know your prefixes. So wavelengths that are greater than red light, so greater than about 750 nanometers, 740 if you want to be pedantic about it, that's what we call infrared light. Until we get to really long wavelengths, and then we don't want to call that infrared light anymore. We'll call it a different color. So longer wavelengths than red is infrared light. And you can remember that what's below red, and whenever we're talking about below means less than here. So we'd have to talk about frequency. So frequencies smaller, or frequencies below the red light frequency. So bigger wavelength equals smaller frequency. So even smaller than that, you're talking about wavelengths longer than red light. You get used to it after a while, I promise. So if we go to longer wavelengths, smaller frequencies than red light, we're going below red, we're going infrared. Okay, let's play the game over here. What happens if we go to wavelengths that are shorter, so smaller wavelength, bigger frequency, if we go beyond and above violet? We might want to say you went ultraviolet. So if you go to shorter wavelengths, larger frequencies than violet light, you go beyond violet and you have ultraviolet light, UV light, stuff that you've heard about, stuff that you've experienced when it gives you a sunburn. So the light that's responsible for giving you a sunburn is not the light that we can see. It's an invisible form of light to the human eye, ultraviolet light. What is the difference between ultraviolet light and visible light? It has shorter wavelengths, wavelengths less than 380 nanometers. We've gone beyond violet. We've gone ultraviolet. And what I want to do for a second is I want to show you that just because the human eye can't see these colors doesn't mean that we can't detect them. So right here, and I'll go ahead and stop my share so we can go full screen. I just have my TV remote. Now, you'll usually see that there's a little tiny light that's in a TV remote. But you can sit here and look at it and press any button all you want. And I encourage you, if you have a remote of any kind, go get one. Find the light on it, click some buttons, and you're not going to see anything. How these remotes work is they send an infrared light that is detected by whatever's receiving it. The camera in your computer or your phone or whatever you're using is not the same as our eye. It can actually detect infrared light, wavelengths that are larger than red light. Only a little bit of them, but it can see infrared. So that means even though I'm clicking this button, I'm looking right now, I can't see anything. If I point this at the camera and I push the button, you can see that a light is coming on. So the camera can see this infrared light, but my eye can't see the infrared light. So you can see the wavelengths beyond visible light exist. They can be seen by other things other than the human eye. Some animals can see infrared. Some animals can see ultraviolet. And they have utility. We can invent technologies that exploit infrared light or any of the other kinds of light. Okay, so let's jump back in. So if we can go to wavelengths longer than infrared light and shorter than ultraviolet, what are all the different types of light? We could talk about the visible spectrum of light, the infrared spectrum of light, the ultraviolet spectrum of light. Is that it? So based off of historical reasons, and by the fact that we didn't realize that all of these were light until basically we understood electromagnetic waves, and we're like, holy cow, radio waves are just another form of light. We can divide the entire electromagnetic light, electromagnetic waves, we can divide them up by their wavelengths from the absolute biggest wavelengths to the smallest of the small wavelengths, and look at all the possibilities of light spread out according to their wavelength. We can look at all the electromagnetic waves spread out by wavelengths. We can look at the entire electromagnetic spectrum of light. And we can see that visible light is just this tiny little sliver. This is the universe that humans can see. All of this over here and all of this, that light is out there. We just can't see it. It's invisible to the human eye. You can only see a tiny, tiny, tiny fraction. And I'm going to come back to that in a minute. But I want to go ahead and give you all the different parts of the electromagnetic spectrum. We have our radio waves, our longest wavelength light. So for biggest wavelengths, we're smallest frequencies. And that's, I'll only do frequencies a couple of times at the radio waves and the gamma rays. So radio waves is the longest wavelengths of light. Notice that this is wavelength in meters. We're talking about hundreds of meters, kilometers. You're gonna have a radio wave that is a megameter in wavelength, a gigameter in wavelength. But typically what we use here on Earth, we're talking about 1 meter to maybe 10 meters or so, to hundreds of meters. So we have the radio wave spectrum. Then we have a little bit shorter wavelengths than radio waves, we have what we call the microwave region of the electromagnetic spectrum. We have our microwave spectrum. Yes, your microwave works by sending out wavelengths in the microwave region of the electromagnetic spectrum. We'll talk later about how those microwaves will interact with your burrito, your frozen burrito that you put in the microwave, so you end up with a hot, tasty burrito. How does blasting a frozen burrito with microwaves make it a hot burrito? So we now have our microwave spectrum. We go to a little bit shorter wavelengths than microwave. So we're heading towards the visible. Oh, now we're in the infrared part of the spectrum. So we have the infrared spectrum. And then we go to shorter wavelengths than infrared, and we've entered the visible spectrum. So we'll go through red light as we move to shorter and shorter wavelengths. Orange, yellow, green. There's that cyan color. Blue, violet. And then we'll move beyond to shorter wavelengths than visible light. And that puts us in the ultraviolet part of the electromagnetic spectrum. So we now have the ultraviolet spectrum. Keep going to shorter and shorter wavelengths. So the wavelengths, those crests are getting closer and closer and closer together. And you'll go past ultraviolet into X-rays. X-rays were named because they didn't know what the heck X-rays were at first. Put a radioactive source on some film and you get a picture that's exposed. And you're like, what the heck's going on here? You got some X-rays flying around as well as other kinds of radiation. But so X-rays were discovered. They weren't recognized to be ultraviolet or to be electromagnetic waves yet. We later on figured out that X-rays are just electromagnetic waves, and they're electromagnetic waves with wavelengths shorter than ultraviolet light. Keep going to shorter and shorter and shorter wavelengths. So you keep moving to shorter and shorter. Those wave crests are getting really close together. So here you're at 10 a trillionth of a meter is the wavelength. 1/10 of a trillionth of a meter is the wavelength. And you're talking about gamma ray light, the shortest wavelengths of light. So we have our gamma ray spectrum. And these are the smallest wavelengths, so they'll be the largest frequencies, the biggest values of frequency. And that's our entire electromagnetic spectrum. It's all the wavelengths of light put out and broken into these 7 different regions. Now, I want to go ahead and just hopefully give you a little bit of a wow factor here. Because let's just take this scale, because we can go to shorter than what's shown here. We can go to shorter wavelengths than 10 to the minus 13. We can go to larger than 100. But let's just use this scale. It's a logarithmic scale. So you can see that it's changing by a power of 10 for each one of these even divisions, which means that if we were to stretch this out into a linear scale, it would be enormous. So I'm going to go ahead and let's imagine that we'll take the radio waves, keep this here at Earth, and then we're going to stretch out the electromagnetic spectrum, and we'll put over here the shortest ones that we can see, 10 to the minus 13, at the sun. And then we're just going to stretch out the electromagnetic spectrum in our minds, so it would go from the Earth to the sun. On that scale, how wide would the visible light spectrum be? It would be about 5 centimeters wide. So this much space between us and the sun, we could cram the entire visible spectrum of light if we were to take the scale that's shown on the screen and stretch it between the Earth and the sun. Just 5 centimeters. Out of that entire 150 million kilometers, 93 million miles. The visible spectrum is very narrow. The light that humans can see, the parts of the universe, the lit up parts of the universe that we experience with our eyes, is tiny. The vast majority of the light in the universe is invisible to the human eye. What we've been working on since we've really had an understanding of the electromagnetic spectrum and been able to build telescopes is We want to see what the universe looks like in all the different parts of the electromagnetic spectrum. Because we can go beyond, we can invent technology that's better than our eye, that can see more colors, more wavelengths than our eyes. And each part of the electromagnetic spectrum reveals new, absolutely fascinating celestial objects, physical phenomenon. It is incredible. It has been an absolute revolution in our understanding of all of astronomy, is the ability to observe the universe in all the parts of the electromagnetic spectrum. So yes, I do expect you to remember radio wave, microwave. This is going from longest wavelengths to shortest wavelengths. Infrared light, visible light, ultraviolet light, X-ray light, and gamma ray light. And this is in the notes, just to really emphasize, yes, for exam 1, you better be able to put these in the right order. I'll say start with the shortest wavelengths and go to the longest wavelengths, or I'll say start with the longest wavelengths and go to the shortest wavelengths. Maybe you have to recognize them all put in the correct order on a multiple choice type question. Or maybe you have to put them in the reverse or recognize them in the reverse order. Or maybe I'll start it and you have to tell me what the next one is, something like that. So be prepared for that. And one last thing before I end this video, a little bit of weird astronomy language. So the way that astronomers talk, we assign a directionality to the electromagnetic spectrum based on the spectrum that we can see, visible light. So let's just plunk ourselves right down the middle of the visible light spectrum here in green light. We say if we're going to move along the electromagnetic spectrum to longer wavelengths, so move to redder light, we say that we're moving in the redder direction, and that extends past just the visible spectrum. So if we want to say what is redder than red, we could say infrared. What's redder than infrared? Microwaves. What's redder than microwaves? Radio waves. I know it's strange terminology. It's so strange, but you get used to it. I've been using it for so long that I had to actually back up and remind myself, hey, stop, slowly explain that we use this strange terminology. So we say we're moving in the redder direction if we move to longer wavelengths. And in the opposite sense, if we're moving to shorter wavelengths, we say we're moving in the bluer direction, towards blue. We don't say the violeter direction because that's a mouthful and nobody wants to say violeter a whole lot. Try to say it 10 times in a row. Violeter, 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 violeter. Okay, it's not too hard, but it still sounds weird. So we say that we're moving in the bluer direction. So what is bluer than visible light? Ultraviolet. What's bluer than ultraviolet? X-rays. What's bluer than X-rays? Gamma rays. Strange terminology, but you'll hear me say it. You'll see it if you're reading anything about astronomy. So I wanted to make sure that you're aware of it, especially since I'm going to be saying it multiple times and I'm going to forget that it's something that is not just common to everybody. Okay, thank you for tuning in. I hope you understand the electromagnetic spectrum. I hope you're fascinated by all the types of light that we can't see, all the technology that's based on it, radios that you can, well, we all know radios are super useful and radio waves are super useful. That's how we communicate. We're using light to communicate, just very long wavelength light. We can use infrared to make technologies and we can see some infrared light. So we have all sorts of uses for technological uses for all the different parts of the electromagnetic spectrum. You don't have to go too far to understand that there's a lot of medical use out of X-rays. Some of you, most of you have probably had X-rays. Okay, I could talk about this all the time. It's wonderful. I'm going to stop. I will see you in the next video.